So if we could begin with a sound check. Can you hear me in the back row? Can you hear me in the back row? I need to be extra careful to talk softly today because I've had a cold most of last week. Before I begin with the lecture today, this is a rather somber anniversary. It is the 4th anniversary of the war in Iraq. And I hope you'll join me in a moment of silence in respect for those who've fallen in these 4 years. It is a sobering thought to think that if we gave each of the fallen 1 minute, we would take the whole class time. To return to something on a more eternal scale, let's talk about oxidative phosphorylation. We had talked about the general overview of it, the idea that it's a series of electron transfers embedded in mitochondrial membranes. Now it's time to look at the details of that process in more closely examined. So the first complex of the sequence, which we might have touched on Friday, but that was a week and a half ago now, is complex 1, and it's going to be the complex that's going to receive the electrons from NADH. And the complex that's needed to do it is this funny sort of footed thing. So this is embedded in the membrane, and it's going to have contacts with the matrix, where it can contact NADH and receive its electrons, and then pass completely, oh yes, I have to tell it what to do, don't I? It's also going to pass then completely through the membrane. And the reason it has to do that, of course, is because it's also, in addition to moving electrons, going to pump protons. The electrons are managed through these complexes of iron-sulfur centers, and amongst the other complexes inside of here, there are flavin mononucleotides that also participate. So it's a very complicated kind of water bucket brigade procedure to get that electron from the NADH to its final target. And if we look at that next target, what it's going to do is transfer those electrons ultimately to ubiquinone. NADH has, in addition to its electrons, hydrogens that are going to be involved, and the net effect of these transfers is for 4 protons overall to be moved across the membrane, while 2 electrons are used to reduce ubiquinol to ubiquinone. The exact protons over here may not be the protons over there. It's a sort of, again, the bucket brigade kind of thing, that one proton at the top may bump another one off and so on down, like a Jacob's ladder the whole way through. But we're starting to build up, or to accumulate protons on one side of the membrane. Notice again the matrix, the innermost areas where the NADH is, the protons are being moved into the intermembrane space. Now, ubiquinol can also receive protons from a second source through complex 2. And this is an enzyme that we know as an enzyme of the citric acid cycle, succinate dehydrogenase. Succinate dehydrogenase was the only member of the citric acid cycle that was actually an integral membrane protein. And in the process of transferring electrons between succinate and fumarate, those electrons get passed into the complex where they can be used to reduce ubiquinol to ubiquinone. You notice that complex 2 does not pump protons. It just moves electrons. Another source of electrons for ubiquinol can be from the cytoplasm, where there may be NADH generated through various processes. And they can get shuttled in through the glycerol phosphate shuttle, in which you again have these sort of reversed oxidations, reductions. But the net effect of it again is to move electrons to ubiquinol, to make ubiquinone. The next exciting moment, or the next big moment in electron transport, is complex 3. So wherever the electrons came from, whether they came from NADH or whether they came from succinate dehydrogenase, they're all going to have to move through complex 3 to get anywhere else. And so complex 3 is going to receive the electrons from ubiquinone. It's going to then transfer them to 2 cytochromes. And in the process, cytochrome B is going to be reduced, and cytochrome C1 will also be reduced. There are also, again, iron-sulfur centers in this case. You can look at this structure and you can see how it has this heme structure that we've seen before in hemoglobin. But it differs. It's got sort of fur off the edges, sort of fringes to make it a little different in terms of the interactions with the protein. And in this case, the iron will undergo cycles of oxidation and reduction. In the case of hemoglobin, we did not want it to rust, and the hydrophobic pocket kept it safe. In this case, we do want it to reversibly rust and get shiny again. Sorry, here we go. All right. So what does that look like? Well, complex 3 is, again, an integral membrane. It makes contact with the matrix on one side and the intermembrane space on the far side. And all the groups inside of it are spatially organized to facilitate the transfer of electrons. What makes life a little more complicated here is that we need different numbers of electrons for the different electron carriers. So ubiquinone can carry 2 electrons at once. Cytochrome B carries 1 electron at once. So we have to do something a little funny to make that work. 2 and 1 are not the same number, so how do we make that go? And it looks something like this. In round 1, we start off with, you can start off here if you like. Here is a reduced ubiquinone with its, in the fully reduced state. And it's going to deliver electrons. And one of those electrons will go to cytochrome B, and one will go to an iron-sulfur protein. The electron that goes to the iron-sulfur protein can go to cytochrome C1 and from there to cytochrome C. So the first electron that we're following can do a very simple transfer down to the next electron carrier in the chain, cytochrome C. And we'll talk a little more about cytochrome C in a minute. The other electron, though, can't go straight there. It's going to be parked temporarily, so to speak, on cytochrome B. And the naked ubiquinone that's the result of the first transfer can receive that single electron and end up as a half-reduced semiquinone. This initial process, this first round, moves 2 protons. Okay, so remembering that we're always trying to move protons from the matrix into the intermembrane space, we've gotten some protons moved at this point of electron transfers. But if we left it in that state, then we would end up having, we'd accumulate the semiquinone and never have any ubiquinone to use for the rest of the things. So in the second round of it, another different molecule of ubiquinone comes in, donates its electrons. In this case, by using the semiquinone for the receiver, we can regenerate a full reduced ubiquinone. So the ubiquinone is not only cycling electrons from complex 1 or complex 2, but it's also acting as kind of a local ferry to accommodate the fact that the cytochromes can only carry 1 electron at a time. In the second round, we also see protons moving. So protons are taken up from the matrix in order to make the QH2, and they're released to the matrix at that point of it. So it's a very effective way to move protons. And in the process, we get out of it 2 molecules of cytochrome C. Any questions about that ubiquinone cycle before I move on? Okay. So, if we look at that sort of as a net process, for 2 reduced Qs that go in, we get 4 protons moved across into the intermembrane space and 2 molecules of cytochrome C. So it's clearly an important stage in the transfers. Now, cytochrome C is an interesting electron carrier. Ubiquinone was a lipid-soluble electron carrier that could carry 2 electrons at once. Cytochrome C is a water-soluble electron carrier that's often called a peripheral membrane protein. And the reason for that is this. You see all these little purpley blobs here. Those are all negatively charged residues, lysines and arginines. So it's an extremely negatively charged molecule. So it's very soluble in water by itself. But when it's exposed to something like a membrane where you have the very positively charged, excuse me, lots of positive charges, but it's basic because it's positively charged. When it's interacting with all the charges on the membrane head groups of the phospholipids in the membrane. It's just sort of rolling along those head groups like something rolling along the sticky side of a Post-it note. So it tends to stay associated with the membrane. It is also very highly conserved. Cytochrome C is not the most conserved protein, but it's a highly conserved protein. And you can see here it has its heme group tucked in sort of in the middle of the molecule so that things won't happen to it except when they're supposed to. So the next step of what's going to happen with the electrons is complex 4. And complex 4 is going to oxidize the cytochrome C. That is, it's going to take its electrons away. And it's going to transfer those electrons to the ultimate electron acceptor, which is oxygen molecules, O2. And in the process, that's going to make water. So that's why when you burn sugar, you release carbon dioxide and water. The carbon dioxide came out at the level of the citric acid cycle, and the water is coming out through the oxidative phosphorylation. If you do the math here, though, the oxygen molecule is going to need 4 electrons, and the cytochrome C only carries 1. So part of the trick of complex 4 is that it can maneuver 4 cytochrome C's electrons around in a stable way to get them all onto one oxygen without anything terrible happening along the way. Here we see a number of copper atoms being active in here. There's a heme A group, and there is a copper-iron complex that's going to be complexed in this. Like the other 3 complexes we've talked about, it's a transmembrane complex, so it has some on the side of the matrix, some on the intermembrane side. Lots of transmembrane spanning helices. Now, how on earth can you play with fire? Because that's basically what the membrane is doing. The oxygen molecule is what makes fires hot. It likes to react. How does it manage to hold on to it to carefully add in 4 electrons before it lets it go? It looks something like this. You have an iron-copper center that's currently in its more reduced state. The oxygen parks on the Fe2. At this point, the complex starts transferring in electrons from the cytochrome C, and you can sort of load up the iron-copper center with oxygen in a couple of different oxidation states. As protons are received in for this one, you can then turn that into a water, of course. Over here you have the O and the 2- state. You don't want that around very long, trust me on that one. So electrons coming in there can again reduce it down to the O- again with more electrons and protons, again another molecule of O2. So both of the metals are important to it. It never lets that oxygen be free because oxygen, certainly in its partial oxidation states, is a viciously active molecule. But it's also consuming protons. And see, it's consuming protons here and here and here. And since it's consuming protons, it has the same effect as removing protons from the matrix of the mitochondria. That's where those protons come from. So in the process of using up protons, it's increasing the proton gradient. Using up protons from the matrix has the same effect as actually moving one across, or half the effect. So it's not so much that complex 4 is a proton pump, but it does increase the proton gradient. So this is looking at this in a more sort of overview sort of way. In addition to the protons that are actually used to make the water molecule, there are others that are simply pumped, that are actually moved through the electron motive force of the transfers that are going on. The electrons are coming from the cytochrome Cs that are on the intermembrane space. They're moving through the interior of complex 4 to the oxygen molecule, which then is making water inside the matrix. So how useful is this process? How much can we get out of it? Well, it turns out to be energetically very useful. At each of the major complexes, so complex 1, which is going to take its electrons from NADH, complex 3, which takes its electrons from ubiquinone, and complex 4, which takes them from cytochrome C. At each one of those, there's a large enough delta G0 prime associated with that drop. You can see these are big drops in energy. There's a big enough energy drop associated that in principle, that transfer should have enough energy to make an ATP. We haven't yet seen any ATPs anywhere on the landscape, but we've seen electrochemical events happen that have an energy equivalent of more than making an ATP. In effect, we've been storing those protons in a battery. We've been making a battery out of the mitochondria. What's kind of slick is that these various complexes are not just rolling around free in sort of like icebergs in a lipid sea. Many of them tend to associate in complexes. So you can see ones that look like this, where you have complex 1, which channels electrons to 3, and then it shuttles them off to these groups of 4, and so on. And the suggestion is that these complexes, sometimes they've been called a respirosome, that these complexes increase the efficiency with which those electrons can be transferred, and that those electrons are never out free where they might do any harm to anything. So we've been talking about moving protons as a highly exciting and valuable thing to do. And the net effect of all of what we've been doing has been to overall reduce the number of protons on the most interior part, the matrix of the mitochondrion, in here, the purple, and to increase the number of protons in the intermembrane space up here, the green area between the inner membrane and the outer membrane. We call this an electrochemical gradient because it has two components to it. It's electrical because the protons carry charge and the properties of the membrane are such that the charge difference is not dissipated. It's also a chemical gradient because there's a difference in concentration of them across the membrane. You could have a difference in concentration of protons with no difference in electrical charge. If we lost a potassium for every proton, there'd be no electrical gradient. But in this case, the membrane is set up in such a way that both the charge and the chemical gradients are being preserved. When you do the bookkeeping and you look at how it actually works, 2 electrons fed in at the top by an NADH molecule from the citric acid cycle, for instance, or fatty acid oxidation, or whatever. 2 electrons in at the top will move about 10 protons. This was discovered by a man called Peter Mitchell. Peter Mitchell was something of a renegade in England. Up until he proposed this model for how mitochondria worked, it was assumed that each of these complexes, which had been more or less identified, that each of those complexes was going to make a high energy intermediate. A high energy intermediate being something like phosphoenolpyruvate or, glycerol 1,3-bisphosphate or something like that, something that had some high energy bond in it. And many biochemists put in many hours trying to find those high energy intermediates. And it was Peter Mitchell who had the insight to say, I don't think it's one molecule. I think it's the mitochondrion as a whole that is carrying this energy. That is, the energy that we see in this proton gradient can't be pinned down to this proton or this membrane. It's a property of the system of the mitochondrion. Unfortunately, Peter Mitchell was rich. And since nobody wanted to do his experiments, he built a lab and paid people to do them for him. And for a number of years, he was the only one who believed he was right. But he kept thinking of more experiments and more ways to test it and more ways to apply it. And bit by bit, the world of biochemistry came around to his view. There's a lovely biography of his work, if anybody likes to read about how mavericks can eventually persuade the world. This electrochemical gradient is also important in another system we're going to study in detail, which is photosynthesis. And so when you get a good sense of how it's working here, you'll be ready for that. It also is behind how bacteria swim, and we won't have time to discuss that, but if you have interest, I can give you references. So, we've made a gradient. We've got a membrane that's basically tight to electrons and protons and everything. We've got a gradient. How do we turn that into ATP? Well, it's done by this rather amazing molecule called ATP synthase, or ATP synthetase. And it sometimes is called F1, F0, ATP synthase because these two parts of it are fairly easy to isolate away from each other. So it's a two-part system where you need both parts for all of this to work. And looking at this in sort of a general way, what we're going to have happen is when protons flow downhill, when they flow from the intermembrane space back to the matrix, the only way they can do that is going through the interior of the F0 component, which is a transmembrane component. And then magically, mysteriously, the movement of those protons through the F0 component is going to facilitate the formation of ATP by F1. So there's some way that these two parts talk to each other to turn that flow of protons into synthesis. And it turns out to be almost like a water wheel, except this is a proton wheel. The overall structure of this has been generally conserved across the prokaryotes and the eukaryotes. That is, prokaryotes also use F1, F0 ATP synthases. The F0 part here, this is the membrane embedded part, as I said, and it has a number of components to it. It has a cylinder of C proteins. You can see the cylinder sort of like here. It also has an A component and a B component. The F1 part is largely outside the membrane. It has sort of a radially symmetric component at the top. The big obvious part, the sort of flower on the bouquet part, is 3 copies of an alpha-beta dimer, plus a delta here and a gamma and epsilon spindle. And we're going to see why there's a spindle sticking up and why there's a delta spanning across the top. So it's a fairly complex little piece of machinery here. This is an actual picture of an F1, F0 ATPase, just looking at it in the electron microscope. And it's really, when you think about the size of that, a marvel that they've been able to get the detailed protein structure that's displayed in this little flower bouquet representation of it. They've made an effort here to try to color code the diagram to the protein structure, so you can see the gamma spindle being purple and the epsilon base being red, and so on. Now, in the membrane, in the F0 part, in the membrane part, one part is going to rotate, the radially symmetrical part, the C components. That is going to rotate. But the A protein is going to be stationary. It is not going to move. So the ring of C proteins is going to rotate past a standing still A part. And what's going to happen is as protons enter the A, they can bind to a C protein. And as it turns in that direction, another molecule of C came by and released its A up that way. So as protons come in here, they bind to the C and get carried around on the ring. As those protons come back in at this end, they touch a different channel, which allows the proton to pop out back into the matrix. So the overall effect is the protons are flowing from the outside back into the matrix, but they're not flowing directly there. They're having a little merry-go-round ride on the C things before they go the rest of the way in. And because there is a strong gradient involved, the direction that it's going to spin is going to be determined by that gradient. So what I've done here is to show you a little blow-up that of the diagram we were looking at before. This part of it blows up to look like that. So that's the F0 part. Now on top of it, the flower bouquet part is a trimer of alpha and beta. So you can see here one alpha and one beta. So there's an alpha beta, and there's another alpha beta, and there's another alpha beta. So it's a trimer of alpha and beta. It's held still by what's called a stator, something that turns as a rotor. You've heard of rotors before. Something that stands still relative to something turning is a stator. And if we back up a little bit. You see here the B part here. This is the stator, the stable, stationary part that's going to connect the A component, which is also stationary, over towards the alpha beta trimer. So the B proteins and the delta things act as sort of, the top part that keeps the thing from spinning out from space. In the middle here, is a gamma. And the gamma is a spindle, and it is actually going to turn. So the alpha and the betas are going to stand still. They stay there. And the B part, B and delta, keep them there. But in the middle of it is going to be this gamma that's going to go turning from the inside of it, touching each part of the trimer as it turns around. And as the gamma in the middle turns, it's going to affect the conformation of each alpha-beta dimer that it's in contact with. So to go back to that diagram, the A is standing still. The alpha-betas are standing still. The B's and the deltas are standing still. It's just this spindle here, the gamma spindle, that's going to rotate. And it's going to rotate because of the C ring. Now, how does turning a spindle inside of a stationary trimer make ATP? It is not obvious why that should work. And yet it does. So let's just start for a moment at any one of the three conditions. Since it's going around and around, you can start anywhere. So let's just start at this particular state. And we have here three different possible states that a trimer can be in. It can be in an open state, a tense state, or a loose state. And in the open state, it can receive an ADP and a PI to come in and bind. In the tense state, in the loose state, it is binds the ADP and the PI and is going to be able to make out of that an ATP. And then, I'm not explaining this well. Let's back off on that again. The three things you need to be able to do is to bind ADP and PI, to squeeze ADP and PI together to make them into ATP, and then to let go of the ATP. And those different things are possible in the different states of the components. So if the gamma rotor is pointing into the dimer in one way, it's in an open state and can take up an ADP and PI. Let's look at that one subunit first. So it can take it up. It has the ADP and PI bound, but the gamma rotor has turned away. It's in a different relationship to it, and the ADP and PI are bound, but they're not yet turned into ATP or anything. They're not going away anywhere. They're bound, but they're not doing much. If we let the spindle rotate one more time, we see over here that it has squeezed the ADP and PI together to make an ATP molecule. And with one more rotation of it, it's back in the open state, and since it's open, it lets go of its ATP. Each one of the subunits is going through that series of changes. So the lavender one here is open and then loose and then tight and then open again, spitting out an ATP. The green one here has an ATP that's made, it spits it out, it binds some more, and now it makes ATP again, and so on. So each of the three subunits goes through this open, loose, tight cycle again and again. And it's driven through that cycle because the spindle is turning around, poking it in different ways. And as it pokes it in a different way, it becomes tight or loose or open. So the energy to do the turning of the spindle is coming from that rotating disc below it. And as it pokes into the dimers that are on the outside the membrane, it can change its conformation, and that can provide the energy to turn ADP and PI into ATP. Are people, does this make sense? Is there anything about this I can make clearer?
So with every turn, is it 3 years?
Correct. Correct. Okay, we can back up a second. So what we're watching here is, actually let's go back here. So here is the whole complex embedded in the membrane. And the F0 part is in the membrane. F1 is attached to that, but outside of the membrane. The protons are going to be moving from the intermembrane space back into the matrix. And so this part of the complex is sitting in the matrix. Okay.
But where, like, geographically is the ultimate disconnect? Is it coming out of the alpha, beta, or where is it coming out?
Okay. All right. If you look at the complex from the side, it physically looks kind of like this. If you look at it from the top, and if you're asking me where on that whole complex it actually binds, I don't know, but people do know, and if you want, I can look it up. There is an ATP and ADP and TI binding site on it, but I don't know the exact location of it. But it is known, so we could find it. Other questions? Okay. Oh, sorry. Yes. This one? Uh-huh. Right. Okay, so the one blue and one green is an alpha beta dimer, and another blue and green is a second alpha beta dimer, and then this one is the third alpha beta dimer. Okay? So on this slide, lavender is an alpha beta dimer, green is an alpha beta dimer, blue is an alpha beta dimer. Okay? I like their color sense. And they also here keep one dimer the same color while it changes shape, which I think is more intelligible than some of the other diagrams I've seen of this process. I did make a request to have flash added, but I haven't heard any response, so I don't think it'll probably be worth taking your time. But there's a very nice animation of this whole process that I have links to in the link section of Icon. So if you'd like to see it made more concrete or visible, I can really recommend that animation to you. Other questions then about this particular part of it? Okay. So this gives rise to an interesting thing. When we're thinking about electron transport and oxidative phosphorylation, there are really two processes going on. There's electron transport, where the electrons are flowing from NADH to oxygen and making water. And there's a second process where ATP is being made because of a gradient. But they're only connected through that proton gradient. That's the only connection they have. They're coupled through that proton gradient. And you can show that if you don't have phosphate, you can bring oxygen consumption to a halt very, very quickly. Well, let me just take a quick look to see if we have figures of that. So one of the major controls on electron transport is the availability of phosphate. And if you think about this for a bit, you can see why. If we go back just to here, if you're not spinning this around to make ATP, you're jamming the flow of protons coming back out. And that's going to change the electrical potential in the whole series, and electrons can't keep flowing. So a continued flow of electrons under most conditions requires a continued production of ATP. And the principal regulation on electron transport is, in fact, availability of ATP and ADP and PI. But we can get around that. It is possible to fake out the electron, the mitochondria, and it's possible with molecules like this. Take a look at these two molecules, dinitrophenolate and dinitrophenol, or DNP. Take a look at this molecule and tell me which of those two forms do you think would be more membrane soluble? Anyone want to venture which one will be more membrane soluble?
Second one.
Exactly. Very good. So this one is the one that's going to be more membrane soluble because it has no charge. It's in the protonated state here. And so it can pretty much diffuse freely across a membrane. And this ionization is one that happens fairly close to neutrality. So what do you think happens if you add this molecule in either form to a mitochondrion or a suspension of mitochondria? Very good. It changes the gradient. Do you want to expand a little on how it changes the gradient? So it can bind a proton, and it can go through a membrane, and it can lose a proton. And it can do those things randomly. And if it picks it up on the high concentration area, and it floats through and lets go of it on the low concentration area, the odds are really low that it's going to find another proton there to take back. So although it's a very dumb molecule, and it doesn't know which side of the membrane it's on average, what it's going to do is pick up protons on the high concentration side and let go of them on the low concentration side. And because it does that, overall, the proton gradient is going to be dissipated. It's going to go away. The electrons can be moved through the transport chain as much as they want, but it's not going to build up a proton gradient. And this is called an uncoupler. It uncouples electron transport from ATP formation. It's no longer oxidative Yeah, question.
The outer membrane is semi-permeable.
Right.
Does it change the gradient? If protons move through that outer membrane?
That's a good question about why is it that the proton gradient stays mostly in that inner area. It may well be that it's not particularly permeable to protons per se. It has a lot of carriers, but I don't know specifically about that. But I think it probably is at least as much mediated by the fact that you have this small space with the surface of the membranes acting as kind of a cage, if you like, for the protons. And then it's in flux. It's not going to hang out there for very long. But I can look into that if you'd like and see if there's anything known specifically about the permeability of protons there. So going back to the uncoupler, when it's present, electrons can continue to flow through the electron transport chain, and oxygen can continue to be turned into water, but no ATP will be made. And so it's no longer oxidative phosphorylation, it's just simply, oxidation. There's no phosphorylation going on. The converse is also true. One of the cute tricks that Peter Mitchell used to show the chemiosmotic theory was if you took mitochondria and put them in acid, they'd start making ATP. You didn't have to give them electron donors. You could just give them a proton gradient, and they would make ATP. This is a drug or a chemical, and I think, in fact, it's actually used as a killing agent under certain circumstances. In the early part of the 20th century, when they discovered it was an uncoupling agent, they got all excited and thought, oh, this will be a weight loss drug. And for a little while, bright people were taking DNP as a weight loss drug because then you could spend the energy without actually, making ATP. But it had the nasty side effect of ruining your kidneys. So it was not a very good diet drug. There are conditions under which it's desirable to have more or less coupling in the membrane. So for example, if you have a honeybee, in the honeybee, early in the morning, there will be intentional uncoupling of the mitochondria so that you can warm up the honeybee. You can use that uncoupled transport to generate heat, and the heat will make the bumblebee warm enough to fly. It's not a very efficient way to get heat, but it works. In other circumstances, you might want there to be less uncoupling. You might want electron transport to be especially efficient. And it turns out that one of the consequences of pregnancy is to stimulate the production of, rather to suppress the production of uncoupling proteins. That is, all of us all the time have a little bit of uncoupling going on anyway. At least we do because we're warm-blooded. And one of the ways that warm-blooded animals stay warm-blooded is they have slightly uncoupled mitochondria. But the energy is being wasted as heat in that case. Apparently, in terms of the total energy budget, it's desirable in a pregnant woman or a pregnant mammal to have more efficient mitochondria, to get the most bang for your buck out of your food. And as you change your surface to volume ratio, the production of heat isn't as much of a problem either. And this is part of the reason why some women actually find it a different food balance to maintain weight. Their bodies actually have become more efficient than they were before they were pregnant, as some of us know to our sadness. So that is what an uncoupler does. If we take a look at just how good these uncouplers or these control of uncoupling can be, if you take this to the uttermost case, the most dramatic example of complete efficiency is in hibernating bears. And so a female bear can retire to the den in the fall, and without eating or drinking from that time in the fall to the time that she comes out in the spring. She can carry pregnancy to term, she can start making milk and survive all of that. And she turns from burning sugar to burning fat. So her body mass had bulked up over the fall to have a larger fraction of fat. She switches her energy metabolism from the glycolysis and cycle that we were looking at and goes to burning almost exclusively fat, which goes again into the citric acid cycle. And the NADH from burning that fat goes into electron transport, which is extremely efficient because she's almost completely tightly coupled. And then in the other sides of sort of making everything keep going, she can reabsorb the water and nitrogen and recycle it into amino acids from her urine, losing 40% of her body mass over the winter. So this is probably as efficient metabolically as mammals can get. But being highly coupled is certainly one part of it. And I think, let's see, that is the last slide of this. Do people have other questions then, either about electron transport or about the recent exam? If you haven't noticed your email yet, Susan has posted the scores for the essays. Those are up. And this afternoon I added them into the total, so it should be present in your totals.
I just wondered what kind of, so I see the 4th hour exams right there on the but I have a fixed type conference that I would really like to go to. I'm not sure that I'll be able to report, but I was wondering how difficult is it to get out of that?
Well, I think for conferences,
Okay. Yeah, it's set up this.
you'll just have to,
See what you get before.
well, or we'll work that out.
Whatever, okay. Okay, it's a while away, so I'm not sure it won't.
No,
Okay.
I've been flexible for meetings.
Great, thank you.
How are things going?
Okay, but I'm not, well, I need some time to search on this.
Okay.
Because I'm not, this is
So it's one of the weirdest. Electron transport is about as weird as biochemistry is. If you master it, you get photosynthesis.
I know, it doesn't sense. I don't want to back up and work on retaking the whole test, but I'm so lost on this actually.
Good luck.
Thank you. Sure, thanks.
Yeah.
I don't remember.
Hi.
But is the final cumulative or is it?
It's cumulative.
Okay.
Yep.
Is it possible to see our last test? I didn't write down the answers that I put on my
I
scan chart.
talked to Susan about it, unless she's left it in the office.
Okay.
I think this fell out of someone's bag that was sitting by me, but I don't know if you want the responsibility of
I think there's actually a lost and found
Is there?
outside.
Okay.
What is it? Is it a,
I think it's a calculator.
it does perhaps it's,
EDA or something.
I think it's too small. Yeah, there is. I'm pretty sure there's lost and found out there. If there's
Okay.
not, bring it back to me and I'll try to go.
Okay.
Thank you.
Could you go over this concept in more time, Computer?
Okay. So, if you have a molecule that it can go back and forth from getting protonated to unprotonated, right?
Yes.
And it can do that close to physiological pH.
Okay.
And so if you have a suspension of mitochondria and you add some of that chemical,
Okay.
in either form. When it's in the ionized form,
Okay.
it's free to move across the membrane either way, right? In the proton, in the protonated form,
Okay.
it's membrane soluble.
Yes.
It can go back and forth across the membrane.
Okay.
Now, let's say it started on one side, it goes across, and it might or it might not lose its proton, right?
Yes, that makes sense.
It's just a chance. If it loses its proton on the high proton side, it's very
Then-
likely to pick it up again, right?
Yes.
But if it loses its proton on the low proton side, it's not very likely to pick it up again, right?
Yes. Yes.
Okay?
Mhm.
And
I understand
Right.
what you explained
Yeah.
so far.
right. And since on the proton side you have, on average, what's going to happen is the transfer will be of protons from the high gradient to the low side, because that's the greatest number. And they'll continue to carry protons across until, on average, they're equal numbers on both sides.
So, are you saying that this compound can act as electron or like a proton carrier?
Proton carrier, exactly. It acts as a proton carrier.
Because it can pick up the proton from intermembrane space, then move across the membrane, then lose a proton on the mitochondrial matrix. Okay. So why is it called uncoupling?
Because it uncouples electron transfer from ATP synthesis. So electron transfer is going, all the electrons going from NADH down to oxygen.
Yes.
That's electron transfer.
Yes.
The F1, F0 ATP is spinning and making ATP. That's phosphorylation. That's making
Yes.
ATP.
Okay.
The only thing that connects those two processes is the proton gradient.
Yes.
Electron transfer makes the proton
Yes.
gradient. ATP synthesis uses the proton gradient.
In order to synthesize ATP.
Right, right.
But
And-
because of this compound can dissipate the proton gradient, it actually uncouples the oxidative phosphorylation. Is it what you're saying?
The oxidation part goes on. Oxygen goes on being consumed, but no ATP is made, no phosphorylation. So if you think of the whole spectrum of stuff, I took that off. So if you think of this whole spectrum of
Yes.
stuff, right? You've got electron transfer, right? And you've got ATP synthesis. Okay?
Yes.
And the thing connecting the two of them is the proton gradient.
Because like if I remember correctly from the textbook, if the proton gradient dissipates, then inhibitor like binds to ATP synthase, right? I'm not sure if I remember correctly.
Yeah,
from the
I don't
textbook.
think, okay, there are inhibitors.
Okay. So what if what happens if the proton gradient dissipates?
Then you can't drive the ATP synthesis, right? The only thing that makes ATP synthesis happen is the flow of protons.
Okay, so even if like a proton gradient disappears, oxidation still can take
Oxidation
place.
is right.
Okay, but no ATP synthesis can take place
Right.
because protons cannot move across the membrane
Right.
anymore. Okay, thank you very much.
Sure. Sure thing. Wakey, wakey. Let's hear. Let's go. This is the slowest computer in my life. Why can't they give me a good computer to teach me? Sorry? Sunday was daylight savings. Classes at 3:30. Biochemistry. I would love to have a life so leisurely that I could manage to not notice. Interesting. Yes, no. Yeah, that was on Sunday. Actually daylight savings was actually last week. It was last Sunday. But since it's been spring break, maybe you haven't had to be anywhere anytime. Right, right. It was actually it is earlier. You're quite right. It's several weeks earlier. Exactly. Yeah. March. No, it's daylight savings, dear. Daylight savings. Well, I'll have the video up on the web fairly soon if you want to watch it. All right. Why is this such a bad computer? It's so slow. I can't believe how long it takes to just change over to showing what drives it has. I put in a request to have it checked for malware and stuff, because even with old things like this, sometimes they get better if you can clean out the spider webs. Wait a second. I must.